Okay, so in this video, we're gonna cover integer arithmetic. And in a previous video, I mentioned that there's two ways that we can represent a integer internally, which is with sign magnitude or 2's complement. We don't use 1's complement. But internally, the machine actually does arithmetic, addition and subtraction, and multiplication and division using 2's complement. So we're not going to do sign magnitude or 1's complement. In sign magnitude, really, even though the machine doesn't do it that way, it could be done by software. So we're going to focus only primarily on addition, subtraction using 2's complement. Multiplication and division have to be done using a different method, which is not covered here. So there are four ways that we can combine two numbers, as you can see here, right? So we have the situation where we have both numbers being positive. We have a situation when we have a subtraction, which is really done by addition, and the b value is actually a negative number. So a minus b is actually a plus negative b. Now, similarly with the third case, when we have minus a plus b, which is really b minus a. So the second and third case are the same. And the last scenario is when you are doing minus a minus b, which is really minus a or negative a plus a negative b. So I'm going to cover all of these four scenarios, even though there's really only three. So the main point is addition and subtraction using 2's complement is really done basically all with addition. So it becomes very simple that the machine can do this in 2's complement, and it's done very, very fast because it's only one operation, it's only addition. Okay, so I have an example here, even though I'm going to do four more. The procedure is whatever the number is, we're going to convert it to 2's complement. So we remember how to do that. If the number is positive, we just represent it in binary. If the number is negative, we have that three-step process. So we convert the first number to 2's complement, we convert the second number to 2's complement, and then we just add. That's it. The answer that we get is our final answer of the addition, subtraction, or whatever it is, in 2's complement. All right, so just keep in mind the following. Let me just show you something here that happens. So we are going to add these two numbers pretty much the same way as we would add a decimal number. Okay, so 1 plus 0 is 1. 0 plus 0 is 0. 1 plus 1, right, in decimal would be the number 2, but this is binary. So how do I write binary in binary the number 2? So the number 2 in binary is written as 1, 0. So it's just like when we're doing 5 plus 5 in decimal, we get 0 carry the 1. This is the exact same thing. So we write 0, and then we carry the 1 to the next step. So now I have 1 plus 1 plus 1, which is 3, or 1, 1 in binary. So we write the 1, we carry the 1. So 1 plus 1 plus 1, 1, carry the 1. 1 plus 1 plus 1, 1, carry the 1. 1 plus 1 plus 1, 1, carry the 1. 1 plus 1 plus 1, 1, carry the 1. So this would be in a carry out bit, which is not used here, but the machine would have it, and we've seen it before. All right, so the effect is, as I mentioned, all we have to do is write both numbers in 2's complement and add them at the end. Okay, so this is regardless if we have case 1, case 2, case 3, or case 4. All right, so let's take a look at one example, or the first two examples right here. Obviously, at the end, you can check, right? So in this previous case, we are expecting that the answer would be -7, right? right? -3 plus -4 is obviously -7. So what we can do to check is, let's represent -7 in 2's complement. So first we write 7 in binary, which is 1, 1, 1. We flip all the bits, and then we add 1. And then we can check to see if these two values are the same. Yeah, obviously are the same, so the procedure is correct. Okay, so let's do the first case. 4 plus 6. So the technique is write two numbers in 2's complement. Let's say that we have a 6-bit field, okay? Now, because both numbers are positive, their 2's complement is just their binary representation. So I'm going to write 4 here, 1, 2, 3, 4, 5, and 6. And I'm going to write 6 here, 1, 2, 3, 4, 5, and 6. Now, 4 is just, this is again 2 to the 0, 2 to the 1, 2 to the 2. So 4 is just this number in binary. So everything else is a 0. 6 is just 4 and 2. Right, to the 0, 2 to the 1, 2 to the 2. So 4 plus 2, 6. And now, all I have to do is add these two numbers as they are in binary. So again, 1, 2, 3, 4, 5, and 6. So 0 plus 0, 0 plus 1. 1 plus 1 is 0. Carry the 1. So 1 plus 0 plus 0 is 1. 0 plus 0, 0 plus 0. And here is my final answer, which should be 10. And let's check. Right? So this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So 8 plus 2, 10. Yep, that checks. So the final answer is correct. All right, let's do our next example, which is supposed to be 8 minus 4. But to do 8 minus 4, 8's positive, and the minus multiplying the 4 makes the 4 negative. So it would be 8 plus minus 4, which we obviously know the answer is 4. But that's okay. We'll do it that way using the addition operation. So keep in mind that all of the different 4 cases are done through the addition operation. So I'm going to write 8 in binary. 2's complement is the positive binary representation. So 1, 2, 3, 4, 5, and 6. So 2 to the 0, 1, 2, and 3. So this is my 8. Right? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3 is 8. And now I have to write -4 in 2's complement. So the -4, and I'm going to do it here on the side, the -4 is a negative number. So I have to do that 3-step process. So the very first thing I do, so here's my -4. 3, 4, 5, and 6. So the 3-step process is first write the number in binary, right? So here it is. This is my 4. Next, I'm going to flip all of the bits. So the 0s become 1s, the 1s become 0s. And then I'm going to add 1. Okay? So 1 plus 1 is 0, carry the 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1, and all of these other ones are just 1s. So this is my -4 in 2's complement. So I'm going to write that number here. And then all I have to do is add these two as they are. Okay, so first, right, least significant bit being added, 0 plus 0, 0, 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 0, carry the 1. 1 plus 0 plus 1 is 2, right? So 0, carry the 1. 1 plus 0 plus 1 is again 2, which is 0, carry the 1. Now, this again, internally would be stored in a carry out bit, which for us here, doesn't matter because it's only 6 bits. So here's my answer. And obviously, we are expecting the 8 plus -4 would be 4. And this is exactly the number 4, as we expect. Okay, so that works perfectly fine. The check was very simple. All right, now let's take a look at the next 2 examples. So the next 2 examples, the answer is negative, right? And we can check them later. But so here's the first question, which is similar to the previous 4 minus 6. It's actually done as 4 plus -6, which should be obviously the answer is -2. So same as before, I am going to write 4 and -6 in 2's complement form using 6 bits. So 3, 4, 5, and 6. 1, 2. Oops, I think I made a mistake here. Let me just make sure that the lines line up so that we won't have a problem adding them up later. All right, so the number 4, I already know. This is the number 4, right? 2 to the 0, 2 to the 1, 2 to the 2 is 4. Everything else is a 0. Now, the 6, again, is a negative number, so I am going to do this on right here, the 2's complement. So first, I write the 6 in binary form, right? So this is 4 and 2, 6. Okay, 2 to the 0, 2 to the 1, 2 to the 2. So 4 plus 2, 6. And then I flip the bits, as we did before. So the zeros become 1s, the 1s become 0s. And then I'm going to add 1. Okay, that's the procedure to turn a number into 2's complement. So add only these 2, obviously. 1 plus 1, 0, which is a 2, carry the 1. So 1 plus 0, 1. 0, 1, 1, and 1. So this is the -6 in 2's complement. So that number, I'm going to write it right here. So 1, 1, 1, 0, 1, 0. And all I have to do is add them up right now. So again, we begin with the least significant bit. So 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, and then 0 plus 1, 0 plus 1, 0 plus 1. So this should be my answer, and I'm expecting 4 minus 6 to be -2. So is this the -2? Well, we can check. All right, so we can check. I'm going to erase this thing for now. And I'm going to check to see if I have a -2 right here. So -2 to 2's complement. All right, so 6 bits again. I first write the number 2 here. All right, so here's the number 2 in 2's in binary. I flip the bits. So the zeros become 1s. The 1s become 0s, and then I just add the 1. So 1 plus 1, 0. Carry the 1. 1 plus 0, 1. Don't carry anything. And then all of these are just 1s. So this is my number, supposedly in 2's complement. It does match what I have over here. So this answer is correct. All right. Now, let's do the last case. And this is very easy because all of the operations can be done with addition. So you actually only need addition to do everything else. Okay, so the last case is -3 minus 2, which is done as I said before, -3 plus a -2, which we're expecting -5. So again, I am going to write both numbers into 2's complement using 6 bits. So I have to convert them both, right, separately. So let's do the -3 first. I write the number 3, right, +3, which is this. Right, 2 to the 0, 2 to the 1. I flip the bits. Zeros become ones. Ones become zeros. And then I add 1 here. Not here. This is the original binary. Okay, so 0 plus 1, 0 plus 0, 1 plus 0. There you go, all the same. So this is the number -3 in 2's complement. So I get that, and I write it up here. Okay, so that's my -3. Now I'm going to do the same thing with -2. All right, so let me erase this. See if I can just erase the digits and not erase the line, so I don't have to do it again. Oh, so that worked perfectly fine. So here is, so I have to write +2 here, right, in binary. So here's +2. I flip the bits. Zeros become ones, ones become zeros. And then I'm going to add 1. So 1 plus 1, 2, which is 0. Carry the 1. All right, ignore this, right? This is the original binary. So 1 plus 0, 1. And then everything else is A1. So this is my number, -2 in 2's complement. So I'll get that, and I'll write it up here. So 1, 1, 1, 1, 1, 0. And all I have to do is add them up. Okay, so 1 plus 0, 1. 0 plus 1, 1. 1 plus 1 is 2, which I write it as 0. Carry the 1. Remember, it's the same thing as in decimal 5 plus 5. 0, carry the 1. Right? This is exactly the same thing. So now I have 1 plus 1 plus 1, which is 3, which is 1, 1 in binary. So 1, carry the 1. Same thing, 1 plus 1 plus 1, 3, which is 1, carry the 1. 1 plus 1 plus 1, 1, carry the 1. So this is the carried out. Internally, there's a bit feud for that. But here for us, this is how we would write the number. All right, so this is my final answer, and we can check to see if this is the actual number, -5. So let's do that. I'm going to do it here at the bottom again. And one final check. So first we write the 5 in binary, right? So this is 2 to the 0, 1, and 2. So here is 5. I now will flip the bits. And I will add 1 right here. So I'm going to add these 2, ignore the original binary format. So 0 plus 1, 1 plus 0, and then everything else is the same. So this is my number, -5 in 2's complement. And as you can see, it matches the answer that we got from the operation. So this answer is correct. All right, so this is how you add or subtract numbers internally using the 2's complement format.